Ahora, Sylvain Fichet, vamos a pasar de escala galáctica a escala cosmológica, falando sobre a matéria escura em uma explicação teórica. Por favor. English, yes.
Eu vou falar em inglês, tá? Vai tudo em inglês, que fica mais conveniente.
Tem que usar eu não trouxe o pointer. Não tem aquele pointer?
Eu?
Você tem o pointer. Vocês compraram o pointer no final.
Rogério.
So in English, it's a model about non-particle matter. I hope you can see the screen. Right. It's okay. So it's a work in progress. Okay, so I call that holographic matter, but I put that with some 2 hours of holographic model of non-particle dark matter, to be more accurate. So it's based on this paper with our friends from Spain, Malaysia, and Mariano Pilos. The last paper that I was talking with master students. It's the published. So, so after some iteration, I will tell you a bit about the technical setup needs. So tell you about whiteboards and similarities and stuff like that. I will make a small parenthesis about a model which not also. Which I will arrive to our proposal. Holographic materiality. Okay. So, what's the motivation? There is a very good motivation. We, as we were, we experiments, so the de-aggregation experiment, which have been for dark matter particle, that have been going on for 1 decades, and they have found such nothing. So there are some excesses, but they are highly debated, and the overall consensus is that nothing has been found. Okay, so no dark matter particle. The experiments are extremely precise, they are amazing, and they still find nothing. So maybe it's a good time to go there again if the dark matter is really made of a weakly coupled particle or of something else. And so our direction is to wonder to come from a strongly interacting sector instead of a weakly interacting sector. Okay? So that's one way to motivate the system. Another way is, the reason is that we actually know how to describe a strongly coupled hidden sector using holographic constructions. We actually have already models about that. So it's a natural and logical possibility to wonder if this kind of construction that we describe a little bit after, it could provide some kind of non-particle dark matter combination. Okay. By the way, feel free to enter me if you have some doubts. Don't have to wait until the end of the session. Just discuss all at once. Okay, so throughout the talk, I'm going to talk about stuff like that. So we have a typical extra dimension, which will be built on chemical words. So you have in mind this kind of metric, so it's very simple metric, which is 5. So flat slices along the x direction, and we change scale when we move along the x direction. Okay. So it's just like the expanding universe, but instead of having the time direction, you have a space-time direction. Okay. And we remind that space stops at some point. So there's a wall. So you can really think of it as a wall, so you can go there, stand on it, you can have degrees of freedom localized it. So usually it's called It's not called wall, it's called brain literature. But really it's just a wall. So I'm going to say brain in the rest of the talk, but can think of it, it's not a big deal. It's just a wall where the space stops. Okay. So I've been mentioning holography a few times. So what do I mean here by holography? I mean fluid. So for any space-time with boundary, something you can always do and separate out the degrees of freedom in the entire space. Yes, very just one dimension. That's so it means that you put the source on the boundary. Isolate out all the bulk, so the entire space, and you end up with where your source is providing some kind of d-dimensional theory. So there is one dimension. Yes. In this you can always do this, just technical, it's just automatic. So now we know to be apart. That sometimes this so you can call this dual theory if you want. Sometimes this dual theory has an independent formulation. So for example, if this side is an anti-de-Sitter, this side will give you control Fichet, CFT. That's the way of thinking about ADS CFT. Beyond the ADS case, there is no independent formulation. It's a rigorous level, exact level. However, from the and from a qualitative viewpoint, there are many things that indicate that beyond ADS, there are still some kind of geometries which describe some dynamics, some complex sharing, at least in some inertial cases. It's more qualitative. For example, if you want to compare about ADS QCD, it's this kind of things. But there are many things that indicate that there's something going on. Okay, so this was a super general. Now, the boundary could be a brain. Space you can have dynamic degrees of freedom living on it. So you can simply say one of this that you obtain a picture like that, where with sharp mixing reverse to 82%. So basically, you can say that your source has become dynamic, dynamical shape. And so you get this picture where you have sometimes called element receptor mixed with strongly coupled. Okay, so that's the one picture.
So
yes,
the idea you have here is that these, what you're calling the elementary cycle does not come from integrating out anything on the wall.
right, doesn't.
This is already localized from the start. I mean,
yes,
they have no. Okay.
Yes, it's already there, and it just stays there. You have
I didn't get the power of the boundary. So you're adding like this extra dimension, but does it mean that like one slice in that other dimension will correspond to what we observe here? Or like I don't understand, I don't quite grasp what's the relation between the boundary and the slice in which our spatial and temporal dimensions are.
So I'm going progressively. Okay, so maybe the next slide will try.
Will you give a specific example?
Specific example.
Yeah, so far it's a cartoon. Like, give a specific example at some point so we know specifically.
Yeah, of course. Then we have an actual model with equations, of course. Just thanks to me without watching. So okay, next slide. Yes, so here you have a bunch of people imagine that you have a bunch of repeated fields. So it's tempting to identify them with sample. In that way, you build a model. An extension of the sample there. where those fields are mixed with a strongly coupled section. And okay, that is what's quite fine. We already have papers about that. So that's a nice picture. And so this is on this side, and if you on the other side, the high-dimensional side, it means that we are localized on the grain. And so this is precisely what we call a brain-worm model. I could have started the whole story just using that, because this is what we are going to use technically in the story. But okay, I think it's nice to have also the dual picture in mind. And its convenience. Okay. So these brain-worm models, they are famous and we studied a lot. However, they have been studied mostly in anti-system. So with anti-system geometry here in the book. While here, the whole point is that we are going to go beyond edges. See what happens. Okay, so this part was just cartoons. Now I'm going to show a little bit more of the technical part. The kind of system we are interested in, it's okay, we can call that dilateral system or scalar system. So dilateral is just a name, just scalar field. It's called dilaton because these calculates are string, more or less a string motivated. So it's a common to call five field. So the setup is that you have each temporary plus a scalar field, which will take a non-zero value.
Sorry, the integral now is over the bulk or just over the brain?
Yes.
Capital D.
Yeah. So here, so I didn't say it yet. This is the bulk action. There is no brain yet.
Okay.
No bulk action. So you have a bulk, you have normal gravity, it's conditional gravity, plus this scalar field. And that's it so far. I put the brain on the next slide. So just to show you a little bit, a few questions they like that, assuming this that's for metric. To solve them, you have to be careful, it's a bit tricky. You have to pay attention to the international instance. For example, here you have three equations. In fact, only two are independent. However, when you are doing the solving, the third equation still remains as a constraint, so like an algebraic constraint or numerical equation constraints. So things can be okay, so the part of constants they are relevant, you can remove them by doing change of coordinates. And possibly, if you do everything carefully, you end up with only one physical scale. Okay. Now I put a brain. So it is that all the fields must have a boundary condition on right, so including the graviton, including the dilaton. So what we do is that put a potential when we stabilize the value of dilaton. So non-zero value. And this fixes the boundary condition for the dilaton. And so this ends up fixing the remaining physical scale, which was a parameter. Okay, so we set up everything is modified, everything is fixed.
So what's the boundary condition?
So the way we do it here is that we put the potential, which fixes the value of the dilaton to a fixed to a fixed value. So it's a TH.
So you fix the value of the dilaton on the brain.
Yeah.
And what about the metric?
The metric is not fixed on the brain. You have Gibbons working term, and you saw using that. So using that, basically the graviton, you can say that the graviton is a Neumann boundary condition in the brain. Any other questions? Yes.
What is this physical scale that you find?
What is it?
Yeah, well.
Oh, yeah, I'm being very general. After we will be more concrete and we will see. We have parameters and so on. Yeah, I'm just being very general. Okay, so now to be a bit more concrete, so now we specify the bulk potential. We will work with this potential along the stuff. So it's this simple exponential potential here. Which depends on one parameter. You have this new parameter in the exponent. It's the only parameter of the model. Call it an M new model.
Sorry, what's K?
Sorry?
K, is K?
Okay. So, okay, you need to have, yeah, right, you need to have some dimension full scales. And that scale is part of it. For example, when you equals to 0, we cover ADS and K will be related to the endless curvature. Right, you have a very dimensions, dimension full scale. So the key parameter is this new parameter. The rest these are just a few dimensional. It's not just only. You end up with one dimensional full scale. So okay, so for u equal to 0, we record IDS. Fine. Another interesting case is u equals to 1. U equals to 1, you recover space which is on the linear dilaton background. And we play a role in the following. Just showing a piece of the solution, which looks like that. It's very simple. You have some powers and with new instruments. Now it's interesting that whenever nu is bigger than 0, you have in these coordinates, you have a curvature similarity at r equals to 0. So the space, since you have a brain, the space is split in two, and the similarity is on one side of the brain, and this is the side we will always focus on. This is what we call an mu minus. So we have brain, similarity, and everything else and does not matter. So this is the picture I will be using for the rest of it.
So R is just one of the directions. What is R?
So R is the what I call C. Yeah, I call it with R. So it's the direction in which the geometry changes of scale. So it's not in that direction. You have a slices of flats. So along this, you have flat slices. Along R, you have a slices change of scale.
What makes R equal 0 singularity? Sorry,
What makes it?
yeah. Why is R equal 0 singularity? Why isn't just an infinite line going void?
So what? If you have a good like the stuff, but it's just one.
Isn't R 1 over C?
So no. So in ATS, R will be 1 over 0.
And that's why the Z equals infinity is singularity.
Yeah, well, in ATS there is a similarity, but so M is 1 over Z in ATS, but beyond that, the connection is not so simple. So you can go to one coordinates, so the Z is one coordinates, but it will be something like X. We don't keep R equals 1 over Z.
Okay, so you don't have a general relation between R and Z for.
Yeah, we have it, but it's I don't have to show it here. It's not going to be useful. The fact that there is similarity at R equals to 0, well, it's just the way it is. I don't have a deeper yes, that. But one thing that is that the dilaton field blows up near R equals to 0, which is sense why there is a similarity there. So everything blows up.
You're saying that this is a solution to Einstein's equation,
Yeah.
coupled to the dilaton field. So the equation that he wrote
Yes,
in the previous slide.
yes.
And this solution,
That,
yeah, but this equation is linear or nonlinear.
it's nonlinear.
So are you neglecting some back reaction or something?
No, it's all exact. All
All
exact. The back reaction is there.
Yeah,
just to be short, I didn't show the Tilaton part solution, but it's also there. Some log and
Potential, why becomes infinite, that makes it a strong couple, is that way then tell us, right?
the potential.
So B becomes infinite, now it goes to zero, right?
You
only find
yes, it's I think yes. So I think
like you have figure out how to work with that, or okay.
so there is so let's continue.
Okay.
And we'll see. So okay, so we have a singularity here. Whenever you have a pure singularity,
Sorry, for new equals zero, there's no singularity, that's what you're saying.
yeah, because it's ADS, yes, there's no singularity. So, okay, so whenever you have a singularity, you should wonder if it is acceptable or not, if it is admissible. People usually say good or bad singularity. That's really the criteria. Now, actually, various criteria, the literature. One is that your singularity is good if it can be hidden by the horizon. It's inspired by the cosmic censorship. Okay, we will see this showing up, but in the last part. You can also think in terms of the fluctuations, so fluctuations of the gravitational background. This part's a bit more messy. So in the literature, there are some discrepancies. We remade our own analysis. We already computed the propagator and so on. And if we get is that the singularity is good if the spectrum has a mass singularity. Otherwise, mean that at low energy, the polarity will decouple, and you will have problem again with the singularity. It's fairly related to the first diagram, but it's done in a very different when the computations are very different. We get this value here. So this is the value for our bundle. We will see at the end of the talk that it matches the one for the horizon computation.
How do you get that value? How do you get the critical value for mu?
So in some slide coming after, you will see it better. But so we compute the gravitational propagator in the index dimension, and we look at the spectrum. And okay, there's some transition going on. And below this value, there is a zero mode, gravitational zero mode. Beyond this value, there is no gravitational zero mode.
So you want less than or equal to BC?
Then
You just told us that if it's less than that, then there is no mass gravity. Is that what you wanted to say?
yes.
So it should be gives you is less than or equal to mu C.
Right. So right. So I mean, some details. So the admissible interval, obviously, so it has the band size goes from 0 to UC, and after that, you can just forget it's a bad singularity. Okay, so what else? Something else which is important in this kind of models is whether the distance between the singularity and the brain is finite or infinite in conformal coordinates. So in this case, we see that for new smaller or equal to 1, distance is infinite. For new bigger than 1, it is finite. Other than that, we can notice that the singularity constitutes a boundary for new bigger than 1, but not for new smaller or equal to 1. This is the way to see that for new bigger than 1, the singularity really, so there is something quite effectively different which happens in the two cases. For new bigger than 1, you theoretically truncate space-time. And these things, they have plenty of concrete consequences. You make more computations.
Why, especially when U equals one, just to. Some, can you show some Lagrangian where you appears?
So one U equals to one is special.
Yeah.
Excellent question. So we have there is some enhanced symmetry there, but it's very small symmetry. It's not very strong symmetry, but there is something there.
You just showed Lagrangian how new appears, and just the only place I saw new was in the potential. Is that the only place it appears?
Yes, before solving, but then it shows up in the matrix. So here, please go to see the matrix. For equals to one, you have r squared here and r squared here. But cancel this. This is this corresponds to the linear dilator.
Right, just we scale five tilde. Well, it's because you fixed the bounding condition of phi tilde, that's why you can't rescale it. So it's something special about U equals one. Okay, let me.
Yes, there is definitely something special, and we saw it in the various papers, various.
I don't think your tilde time just means you have an exponential phi tilde. I mean, it doesn't matter about the coefficient, it's on the collinear until it's correct. Maybe I don't know when you call linear tilde.
So yeah,
You said linear dilettante is just when U equals one?
yeah, like linear dilator is just a name, but
Why do you use that name? I know what linear dilettante is, but why use that name?
it is the dilator will be linear in some coordinates.
Yes.
Not this one's. This one's the log of r. And
When U equals one, it has that property, but for other values mu it doesn't. That's the same. When U equals one, you say phi tilde is linear in some variable, but when U is different from one, it's not. Is that
okay. I think this distinction is but linearity or not, it's not a about it. It's this is just a name. And yeah, that's it.
It would be helpful to have a solution phi. Into the brain.
Yeah. It's like new log r. It's
New log
new,
r.
so it's not super.
Okay.
It's done. Give an example of what I was explaining here. Let's have a look at the spectrum of fluctuations. So with fluctuations in the range, you have to be very careful with gauge fixing. There's some confusion about that in the like. So here, okay, you put fluctuations. Files them, but some of them are related. Okay. So it's a tricky business, you have to be very careful. Using that, you compute the gravity propagator. Here, showing the brain-to-brain gravity propagator, specifically, just to have a simple form to show. So this is it. For new smaller than one, it takes slow. For new bigger than one, there's slow. And then you look at the poles to see the spectrum of gravities. And so for new smaller than one, you get continuum. For new bigger than one, you get certain discrete poles. You can call that discrete. And finally, for new equals to one, the expression is not here. New equals to one, you get what we call a gap continuum. You get a discrete, meaning isolated node, and a continuum of that.
And the isolated mode is zero mass.
Not necessarily. So in this case, yes, because it's a graviton, but in general, it can be different. It can be this. As not be massive. It can be even inside, more or less inside the continuum. Okay, so so it's just a way to illustrate the qualitative changes which occur in this three cases.
You found this just analytically or you did some computer? How did you find these?
It's analytical, it's not analytical. The nice thing of Snowden is that you can solve everything analytically. The green functions, the thermodynamic, and it's a nice simple model. Okay, so that's it for the general formal part. Now we make a little round of this. See that so if you see this gas continuum, you might remember that there has been a model of non-particle dark matter which tries to use a gas continuum spectrum. Let's talk a little bit about it. It's called continuum dark matter. It's made by our friends from the US. Some of them visited IFT. First line of the abstract is that we initially study dark matter based on the gas continuum. Dark matter consists of a mixture of states with continuous mass distribution, blah, blah, etc.
But this is the unparticle idea of Georgia, I know.
This is, in a sense, it's very much like the unparticle idea of Georgia, just a modified name because people don't like very much the particular name. So now you could continue. But
With the exception of the gapped state, right? That's the, right, in the particle business, there was only the continuum. Yes.
so not really. So in a particle business, you can choose whatever you want for the spectrum, and you can choose a gapped spectral density. There are papers like that. So
But that state below the gap looks like a particle.
yeah. Actually, I agree. So it's very similar. Okay. So, but basically, they try to make a non-particle model of that matter. So let's try. Let's have a look at it. Just one slide. Okay. So in practice, in first part of the paper, we write a 40 object where there is a field continuum. A field which has a continuous spectral distribution. So this is the new continuum.
I don't know the project. Just what does continuum spectrum mean? Is it mass is undetermined or?
So you take define a field whose spectral distribution is continuous instead of being discrete.
Spectral distribution is its mass.
It's more general than mass. So if you have an interacting QFT, there's always a continuum part because of the interaction, because of the multi-particle states.
So it just means it's coupled. But then what do you mean by spectrum? It's not a field theory. Spectrum. Spectrum is some eigenvalue, right? Eigenvalue of what operator?
Of the mass operator.
Okay, so the mass is undetermined by its equation of motion. That is.
Yes, I think now it's clear to reply precisely to the question. But if I can do something quick.
But correct me if I'm wrong, isn't it just that you can view states which are eigenstates of energy and momentum, but they don't satisfy the energy, the special relation, relativistic particles. So there's no number for the mass. Vary continuously and have any combination of energy and momentum eigenstates, right?
Why is special relative?
It doesn't, it is not a particle with doesn't satisfy the relativistic dispersion relation for a value of n, yeah.
Okay.
That's the case, right?
It's not a fundamental part.
It's different points, but okay, because you a little bit, and then we that's what I have a much more precise backup slides, but it's actually again because that's too much for us. For us, okay, we just have to feel. Okay, just to feel that they write a form of object. There is some operator. Whose if you take the point function and if you take the its specificity, you get a continuous solution. Okay. So done that, they want to have an interaction between some player and the possibility, so they just write that. They are not important for the argument they're going to make, so let's just forget it. So really, we just have a frequency. By the frequency harmonic, I will just repeat. It's a theory with the field, but the field, so it's a free field, but the free field has a continuous spectral distribution. That sounds weird. Sounds weird. So what's the problem with that? In fact, if you go on the former slide, this thing, that I call a frequency here, doesn't donate, it's called generalized free field. We say GFT. And it's very well known that GFT cannot couple constantly to Einstein gravity. Okay. You can show it in various ways, various levels of rigor. I put everything in backup, otherwise it was too much here. Just to give examples, you get a GFT if you take a CFT with infinite number of colors, keeping the thing fixed. You get a GFT if you take a Holographic and set all the bulk couplings to 0. In both cases, some problems appear. Here appears because if you set the number of freedom to infinity, means the scale of your algorithm theory, so the cutoff scale of the cutoff theory, goes down to 0. It's called a specific scale. So this doesn't work coupled to gravity. In this case, if you set all the interactions to 0, it means you are removing gravity work. So this in this limit, you don't have gravity. So again, you cannot copy. Okay, so it was much longer than I expected, but okay, I have see that there is some problem here. And this problem, if you want to do a dark matter model, because if you do a dark matter model, you want to have gravity obviously. So what's the way out? The thing you can do, and I actually do in the second paper, is to consider an holographic framework. In this case, okay, everything works fine, and what happens is that you have a deviation to standard gravity. That's why you have to debate that with. However, they didn't treat in this framework the finite temperature or cosmic aspect, which is a pity for that matter paper. And it's a pity because this is where the best part comes from. And so this is what I'm going to do now. In the sense, the Google can be seen. So what we do here can be seen as the correct treatment of their initial proposal. Okay, so when you have a gravity, when you pick up rainfalls, if you have a temperature, you must have a black hole in the web. Okay. And this is what they didn't do in the continuing data topic. So we must think about black hole. Black hole solution in a model. So the planar black hole solution is very simple. Found it, it's just like that. For example, the temperature associated is 4. And I will go on about the thermodynamics of this of this black hole, and it's not the focus of this. Just here, there's something you can notice that if nu is too big, it doesn't work here. And in fact, this corresponds to the limit of the horizon and being able to exist. So if nu is bigger than this value, singularity can be discrete. So you have a bad singularity. And the value we get here is just the same as the one we get for the propagator. So everything is nicely consistent. Okay, so moving on. You have a black hole. Now the next step is to compute your dual theory in the presence of a black hole. And to do this, we have a well-known formalism developed a long time ago. I call that wormhole inspired energy. You have various ways, equivalent ways to start it. You can just the closed equation, or there's also the differential condition. You can also think in terms of boundary condition for graviton. All of this, it's just a matter of viewpoint. All of this gives the same result. And we end up with this an effective action for the an effective Einstein equation, which looks like that. It looks very simple. We have a stress tensor, which is just for the well-localized matter, if you have some. And another stress tensor, which contains all the non-trivial effects coming from the body. And that's it. Okay. So there will be other terms, but as long as it's time negligible, actually in practice is super easy. We are just left with that. So it's a familiar looking Einstein equation. So now what's inside this guy here? We have various contributions. There's a contribution from the curvature. There's a contribution from the 5D stress tensors. The latter contribution. So one is for ADS, for example. So potential distribution. Okay.
These are all temperature independent.
They are all, so this is temperature independent. The other ones are temperature dependent.
Where is the dependence?
You will see in the next slide. Guys, just to be very brief, just to show you by terms. So what happens when you combine all of this? The effective tensor takes this form, so form of the perfect fruit. So we have energy density, so effective density and effective pressure. What's inside there? We need to split them into two parts. So that's what we call vacuum parts. She's just constant. Okay, it doesn't depend on nu, nor on the polarization condition or gravitation. It's just constant. It's cosmological. Basically, it gives, yeah, the interesting parts. The other part. The other part depends on nu, on the polarization condition, on the gravitation, and we get this kind of dynamics. We have like limits. It turns out it's the same for both sides, which means your fluid has a simple equation of state. Equation of state is just y minus d squared over 3.
D equals 2, D equals 4, or
Oh, right. So here it's written somewhere, but I put d equals, so big D equals to 5. Because now we are trying to do something on get a faulty. But the same story works for other dimensions. There is nothing special with this dimension. So now let's see. If you have a planar black hole in the bulk, you get a fluid with this equation of state possible in your dual theorem. So okay, so just to be exact, and just to be precise, principle when you put a black hole in the bulk, this is not the only consequence. The general ways of saying this that you are putting the dual theory in the Fermat state. And this, for instance, it's one consequence of the simple mistake. But this details do not matter for us. For us, just have a black hole means created in the
So normally, at least the tools that I know about quantum systems, not just classical, how do you compute dual theory? You know what dual theory is?
so
Who told you that that's dual theory?
by what I'm calling dual theory, it is okay. We integrate out the sugar. However, here we are on the classical level. So it's a classical approximation of this process in this house.
I don't even know what that means, but you integrate out and somehow that. How do you see that it's dual theory for the equator state? How does that come out?
So it's so it's you compute the generalities that you compute the quantum effective action localized in the brain.
Who computed it? You computed it, or did somebody tell you that? Or how did
So
you get to that?
that's the general idea. In general, it's complicated, but you can make mathematically. And the leading order functions, so it's just a classical order function, corresponds to just using the Einstein equation, actually. And yeah, sorry, I'll show you something here. Just using the Einstein equation and the bombshell bulk, and see what happens in the long introduction.
I mean, but this is unrelated to ADS-CFT, or is it related to ADS-CFT?
It is. So
ADS-CFT is very difficult. If you don't have ADS, you don't have your symmetry. Is it yes, or?
no, so in ADS, and people have done this computation in ADS long time ago.
Without supersymmetry?
Without supersymmetry. Yeah, yes. So you just have ADS and use general relativity.
Who are the people, just so I have
Formula.
who are the people who, just so I have an idea of when you say people?
There are many references. I can tell you later.
Okay.
Right now,
Yeah, I know the supersymmetry part, I don't know the nonsense thing.
yeah,
Or 10 minutes.
10 minutes. Move on and so okay. So let's have a look at this subset. If nu is 0, so it's ADS, get omega equals to 1/3, which is responsible for radiation. So you recover the well-known result that the ADS of the world has features that radiation, which is a problem of the levels. Don't want that radiation. If this can be also calculated in a more informed way, saying that the fluid is well, so the CFT at planet temperature features the fluid which behaves as a radiation. Because it doesn't mistake. When you go to 2, which is the critical case, okay, the fluid behaves as a similar constant, okay, no superplastic. Now, for nu equals to 1, you see that omega equals to 0, which corresponds to pressurized matter. Pressure, one issue states. So this linear datum case looks quite interesting. It will make a model of that matter. So let's move on with that. We are going to study the linear datum grand one. Okay. Just to say briefly, if you want to study the cosmic evolution, well, the trick you have that you let break the whole in time, and this produces the evolution of the universe localized in brain. So this coordinate we have the position of the brain is simply the scale factor. And so the Hubble factor is just related to the velocity of the brain in the but sorry.
Yeah, very nice question, but why can you use the holographic principle outside the ATS?
Why?
Yeah,
So we are just doing computations. There is no assumption or some hidden principle. It's just computation. So we are the ideas about it. And what you want is to compute the quantum activation on the brain. This at the leading order, you put the bulk degrees of freedom on shape. So basically, you put the equation to motion, solutions of the equation to motion in your action.
yeah. I thought that the dictionary that you have between the book and the brain worked only for ADS.
Right. Absolutely, I agree.
So why can you use for me larger than zero?
So I'm not using any dictionary, I'm just doing computations.
Okay.
If there is a dictionary, it's very non-trivial and that's it to the dog. No, it's not training any models. It's not just computations. Okay, so moving on. With all that, I'm going to arrive to a nice result. P abundance is given by a simple formula in this model. So as a homogeneous model. And there is no problem to match that to the observed values of abundance.
Well, can you remind me what's RB, RH?
Yeah. So RB is brain position, RH is the brain position, RH is the horizon position. This theta is a physical scale, and H is the
So they were never in thermal equilibrium or anything with the standard model. Do they couple the standard model of particles? Is dark matter unparticle?
no, there's no notion of thermal equilibrium.
So they do not couple to standard model. Only to gravity. They only have the only interaction is gravity.
So we can discuss more about that, but I'd like to move to specific trivia in 10 minutes.
Now, Barbara.
It's supposed to be short. Okay, so here I want to say that this framework is very consistent, very solid because it can make constantly checked, for example, using the 5 equation. If it works out, you have like non-trivial expressions for it to work out, it's very nice. However, this is just a result of the homogeneous model. So if you really want to make a dark matter model, you have to think what's the information and so on. That's much complicated. In particular, you would like to find so the first step for me to be sure that hollow-like solutions actually exist stable. Otherwise, you cannot sure you will go far. And so we are going to do that. We are looking for solutions which will spherical solutions, which will give some over density in the brain. It's a work in progress because it's done before. So apart from that, you can also wonder about the modification to gravity, because framework models, we have always modification to gravity, because gravity travels into the bulk. And okay, so the point on velocity and so one here, but the continuum part here, and this continuum part contribute to the function. And what happens is that because the gap, it shows this modification shows up only at short distances, not at long distances. So there is no, there's only a mild modification to the property with this bar parameter. It's not a big deal. It's the same thing as for the ATS robot. Very mind bound the parameters.
So I didn't understand this part because the gravity is in the 5D, right? Or
Yes,
just
gravity is everywhere.
so you should see some deviations from Newton at long distance, right?
At so you see it at you have to be careful with that. It's not so trivial if it shows up at long distances of short distance. In this case, in this geometry, the unification shows up at short distances, but I think you might have other geometries where deviations also appear at long distances. Okay. Just and finish it. Last slide. Apart from that, you can think about other effects. Yes, for example, what would be dark matter decay? If you have to think about the outcome decay of the black hole. It will decay back to gray. And it's actually a well-defined computation. That's slide is just to do this. After that, you can think about laboratory signatures. Yeah, when the colliders and so on. This part is more or less done because we have basically all the bulk fields which are they always feature a gap fields, they're always the same spectrum. And that the collider, what you expect is that the missing shows up above a certain scale. But we don't have too much to bring about it because this is already treated in the continuum paper. And also, it's more or less like all the unparticle particle models where people already thought about all this kind of things. And finally, as far as we see, none of you is based for direct detection, which is nice. And so here's the summary. You want me to stop now? Or?
50 seconds.
Seconds. Okay. So, okay, just read it.
One would expect that the perturbations would be different from perturbation in usual cold dark matter.
So at the
Because this is a pressure in right fluid.
alright, so at the perturbative level, we thought about that, and apparently there's nothing special going on. The most tricky part that the nonlinear level. That's why for me the most important thing is to make sure if there are really
So how are you dealing with the nonlinear level of perturbations? Are you
well you have simulation, but
simulation?
I can't say much more about that. For me already, that's why my focus for now is to see if at least a final state of the evolution will exist or not. If you see if we see end state, that's it. Yeah. Not have to go further.
Would you explain a bit better how, what are these signatures that you could use to verify this model experimentally?
So, signatures. So, you could look for a small deviation to gravity at very short distances. You could look for, but we have to compute. You could look for the consequences of this dark matter decay. Maybe it would be some kind of dark CFB or something like that. I don't know. See. You could look at colliders. search for reproduction of this continuum of this continuous spectrum. So typically, it could be missing energy, so some energy vanishing to nowhere. Or you can have this continuum in so in internal so in scattering processes where continuum is internal lines. And so this modifies expected processes at layers, and so you can search for that.
Still on that point, you say that all bulk field propagators have this gap continuum, right? But the standard model fields are not the case, right? They are just living in the grid.
Right.
Or do you have this gap continuum for the standard model fields?
So yes, here in fact I was being quick. Both options are fine. If you want, you can decide that all your standard fields, they are really bulk fields. The isolated mode visible somewhere we know, but each of them will be accompanied by a continuum at short but only at high energies.
And the gap is the same for
Yes.
quarters, the same
Yes.
for it only depends on the
Maybe there is some order one factors, but yeah, the scale, the gap is the same for everybody.
Ok, then thanks, Sylvain. Ora, vedo molto avanti e ne riconvine.
Yeah.